Hi everyone and welcome back to our lessons, and in this lesson we will look at exponential equations. Now don't forget, any equation we're trying to solve for the variable. The only difference between exponential equations and the normal equations that we do is that now the variable is an exponent, and to solve for that x that is an exponent, we're trying to make the bases on both sides exactly the same number, because if the bases on both sides are the same, then the exponents will be equal. So what I'm really trying to do is we want one term equals one term, and then we want to make the base on this side equal to the base on that side. So we cannot change the 2, but we can change a 16 so that it looks like a 2. And that's what we're trying to accomplish here. So remember, with equations, we always want one term equals one term, so that we can solve for the variable. When the variable is an exponent, we try to make the bases on both sides of the equation the same, because if the bases are the same on both sides, the exponents will also be equal. Now here are the steps. Move your constant terms to one side. Well, a constant term is one that does not have a variable. So that's not a variable base or a variable as an exponent. So this 16 is my constant term. This is a variable term because x is the exponent in this case, even though the base is just a number. This will be a variable term because the x is in this entire term. So move your constant terms to one side, boom, it's on that side already. Now move the variable terms to the other side, well, it's on this other side already. And then simplify both sides. Well, there's no exponential laws I can do here, no other simplification. Okay, so now try to make the bases equal with the exponent laws. Now look what we will do with this example. Now I already have my 2 to the power of x here, and I'm trying to make the bases the same, and I'm going to try and use my exponential laws to help me. So a 16, I can rewrite it as a 2 to the power of 4, right? Okay, because I break this up into its prime factors, which is 2 to the power of 4. And now look very closely. It's one term equals one term. That base is a 2. This base is a 2. Therefore, I can kind of just throw these bases away, and then we know that x will equal to 4. Because if the bases are the same, the exponents will then be equal. So, we didn't really have to use an exponent law, we just simply used the product of its prime factors. Sometimes we are going to need to make use of exponent laws and definitions, like in this example. Again, we already have the variable term equal to a constant term. But now, I want to make 1 over 49 equal to 7. So here we have basically 7 to the power of x, which is my variable term because x is in this term, right? And when x is an exponent, we're trying to make the bases the same. So let's use a definition quickly. Or we first rewrite the 49 as a product of its prime factors, which is a 7 to the power of 2. Okay? I'm not lying, because 7 to the power of 2 is 49. Do you see I didn't make it a negative 2? 7 to the power of 2 is 49. Okay, if I made that a negative 2, I get another 1 over 49. Okay, so please make sure that you just rewrite the 49 as a product of its prime factors, and you write it in the correct place. It's underneath the line, it stays underneath the line. Now, this is still not a 7. Now I can take all of this and I can rewrite it as a 7, because I can say that 7 to the power of x is the same as 7 to the power of negative 2. Because if I take this base that has a positive exponent, I take it out and I put it above the line, that positive exponent becomes a negative exponent. It's just the reverse of my definition that we learned in our exponent lessons. Now, the bases both are a 7, so therefore if the bases are the same, those two are the same, then it means that my exponents will be equal. So x is equal to a negative 2. Okay, great. So how about this example here? Now, please don't forget this step number 3, because here I have my variable term and there's my constant term. But that x belongs to the 3, not to the 2. So this is actually a 2 to the power of 1, right? Okay, so I just put it there so you can see that's not part of this entire variable term, and I can simply divide with this 2 on this side because this is the same as a coefficient. Remember when we had, and I'll quickly write it here on this side, when we had something like 2x equals 8, then we said that it will be x equals 8 divided by 2 because we always divide with the coefficient on the other side. Now, this is the same as a coefficient because this is an entire number, and a number on the other side can always be divided by a number. We cannot divide with the 3 because the exponent is an x, okay? But here we can divide with 2 because that 2 to the power of 1 is just a 2. So this is the same as a coefficient. So now I have 3 to the power of x equals 18 divided by 2. So we write 18 divided by 2. So we've got 3 to the power of x equals 9. Very important. Divide with the coefficient of the variable term. That is the coefficient of the variable term because it's just a number with a number exponent. And numbers can always be divided with numbers, right? We cannot divide a number with a number that has a variable in it. So here we go. So this, for instance, we want to make the 9 same as a 3 because now we've got the variable term equal to a constant term. It's one term equal to one term. We want the bases to be the same. So this will be 3 to the power of 2. My bases are the same. So therefore x equals 2. Now let's go and look at this example. Again, we've got 4 to the power of x equals 0,25. So 4 to the power of x equals, and rewrite this decimal fraction as a proper fraction. So that will be a quarter. And now a quarter is still not a 4. But we can use one of our definitions to change that. So this will be 4 to the power of x equals 4 to the power of negative 1. Because if I take this 4 to the power of 1, which is a positive 1 there, and I take it out and I put it above the line, the sign of the exponent changes. You remember that, right? Okay, so now we just use the reverse to get the negative so that our bases will now be the same. Because a quarter is not the same as a 4, but a 4 to the power of negative 1, well, now I have the same basis. So this will simply be x equals minus 1. Now, we get to the last example. Now, here I said, move your constant terms. Well, there is no constant term here. But we still want one term equals one term, especially when we are busy with equations with exponents that are variables. So here I've got one term equals to one term, which is good enough for me. But now a 8 and a 16 are not the same. So we want to make them exactly the same. So let's just break this 8 into its prime factors, which will now be a 2 to the power of 3. Put it in brackets and leave the exponent. Do you remember we did this in exponent lessons? And then equals, this will be 2 to the power of 4. Keep it in brackets x plus 1. I didn't change anything here. I just rewrote the 8 as a 2 to the power of 3. And remember, when we change something, we put it in brackets so it represents the same value and the same number. And don't forget about the exponents on the outside. Same with the 16, it's just a 2 to the power of 4 in the place of the 16. Don't forget the exponent on the outside. And then we follow our exponent laws. It will be the 3 times the x and the minus 1. It will be this 4 times the x and the plus 1. So we simply write the base. We get 3x minus 3 equals, we write the 2, we get 4x plus 4. Okay, brilliant. Now, the bases are exactly the same. That's a 2, that's a 2. So I can kind of throw them away. And then we know that 3x minus 3 equals 4x plus 4. And then move all my x's. This is just a simple normal equation, one from grade 9. So we move the 3x to that side. It becomes a minus 3x. So 4x minus 3x is just a 1x. And then here we have a minus 3. If we take that plus 4 to this side, it becomes a minus 4. Minus 3 minus 4 is a minus 7. And x equals minus 7. Okay, so that is easy enough. So what are we trying to accomplish? We are trying to get it to be one term equals one term. Whether it is two variable terms doesn't matter. And then after we make it one term equals one term, we're trying to get the bases to be the same number. Because once the bases are the same, then the exponents can equate and we can solve for x. Same as here. Here we have a variable term equals a constant term. It's one term, one term. We're trying to get the bases to be the same. Once we get the bases the same, the exponents will be equal. Same as here. Okay, so look at all the different kinds. If we have a decimal, we change it to a proper fraction. We change the proper fraction so that it equates the base on the other side. And once we have a proper fraction, we're trying to rewrite big numbers so that they look like a 7, but they're still not the same as a 7 if they're written as a fraction. So we move it with one of our definitions so that we get the bases to be the same. Once the bases are the same, the exponents will be equal. So don't forget these steps. We also want to always divide with the coefficient of the variable term, like in this case or this example. We want to divide with that 2 first before we start equating or getting the bases to be equal. So I hope you could follow, and let's just quickly go through a couple of more examples. Now here are a couple of examples that you can try, and please remember we always divide with the coefficient first, right? Now this is a coefficient, this minus. It's a minus 1, so we want to divide with the minus. So this will be 16 to the power of x equals 32, because a minus 32 divided by a minus 1, which I can put at the front here, or just a minus 32 divided by a minus is a positive 32. One term equals one term. We want the bases to be the same. Why? Because x is an exponent. So this will be 2 to the power of 4. Leave the x on the outside. And then this will be 2 to the power of 5. And then we use our exponent law. So we write the 2. 4 times x is 4x equals 2 to the power of 5. My bases are the same now, so I can cancel out the 2's. 4x equals 5, and we want to solve for x. X now has a coefficient of 4, so x equals 5 divided by 4. And remember, once we divide with the coefficient, we never change the sign of the coefficient. We take it just as it is. So if that was a minus 4, we would have divided by a minus 4 on this side. Don't forget. Okay, and that's the answer. And how about the next example? Well, the base here is a half to the power of x plus 1, because everything in the brackets belong to that exponent and not the 2, okay? The 2 is a coefficient of this base. So basically we have a half to the power of x plus 1 equals 16 divided by 2, which is 8. Now, this doesn't help me because we want to get the bases to be the same. And I know I can change a half so that it can become the following. It can be a 2 to the power of negative 1. And then don't forget, leave it in brackets. And we still have the x plus 1 on the outside. And an 8 becomes a 2 to the power of 3. And now I can multiply that minus 1 in. So we have 2 to the power of minus x. And minus 1 equals 2 to the power of 3. Now my bases are the same. So with that 2 bases, and we know that minus x minus 1 equals 3. So minus x equals 3 plus 1, which is 4, because as we move the minus 1, the constant term, to that side, it becomes a plus. 3 plus 1 is 4. And now we want x. And the coefficient here is a minus 1, so we divide with a minus 1 on this side. So 4 divided by a minus 1, x equals minus 4. You didn't have to put in that step. I'm just showing you that that coefficient is a minus 1, and we need to divide with the coefficient on that side after we move the constant term. And that's it. So how about the next one? Here we need to think a little bit. We've got one term equals one term, but I can simplify this term. If you go back to the earlier part of the lesson, it says there, we always try to make it one term equal to one term, and then we simplify the left and the right side. Now here I cannot simplify yet, because when we want to multiply two things, the bases must be the same. So this basically becomes a 2 to the power of 4. Keep it in brackets with the x on the outside, times 2 to the power of 4x equals, and I'm just going to change this to 1 over 2 to the power of 2, and that is exactly the same as a quarter, right? So here we apply the exponent law, so we get 2 to the power of 4x times 2 to the power of 4x equals 2 to the power of negative 2. And now I can keep simplifying this side. When we multiply and the bases are the same, I write my base, which is law number 1, write the base, then it is 4x plus 4x, which will be 8x equals 2 to the power of negative 2. And now the bases are the same, so now I know that 8x equals minus 2, x equals minus 2 divided by 8, so x equals minus a quarter. And that is all there is to it. So work through this lesson. Make sure you can see the difference between normal equations and when we have exponential equations. That is when the x is an exponent. And we're trying to get the bases to be the same by using our exponent laws and definitions. Once the bases are the same, it means that the exponents will then be equal and we can solve for x normally. Hope to see you again soon. Bye. This is your host Richard T, and thank you for joining us. Please visit our website mathsa.co.za for free guided exam tutorials.